So over the break, I was corrected. It was 185 here, so, and the result came out a little closer to 3.2. But even at 3.15, it was pretty good. So 3.18 is even better. Oh, we're going to take a look at another problem here from the book. This is number 86. This is here. Well, the reaction for number 86 is 2 iron 3s, and this is mercury. Hg2 2+ is called mercury 1. And so we got iron 3, mercury 1 yields iron 2, mercury 2. This is an example of a redox reaction. The oxidizer in this case is iron 3 on the left. The oxidizer on the right would be mercury 2, and it looks like which one's stronger? Yeah, it seems like well, actually 10 to the minus 6 favors the reactant, so it seems like mercury 2 is stronger than iron 3 since it favors the reactant. Well, anyway, I have this 2 iron 3s plus a mercury 1 goes to 2 iron 2s and 2 mercury 2s. Kc is 9.14 times 10 to the minus 6. And so the initial concentrations are given here. The iron 3 and mercury 2 are 0.5 thousand. The iron 2 and mercury 2 are 0.03 thousand. 0.5 thousand, 0.5 thousand, 0.03 thousand, and 0.03 thousand. Looking at that K value, it favors the reactants, right? It's a small K, so it should favor the reactants. And so, which way should this shift? In other words, you know, we don't have any zeros, so otherwise we go to the side with zeros. So there's no zeros here. Is it going to be minus 2x minus x plus plus, or will it be plus plus minus minus? You'd think it's plus plus minus minus because of the small k value. But what we have to do is we have to be careful sometimes. I mean, Kc was 9.14 times 10 to the minus 6. It's pretty small. And this is going to be the ratio of the products to reactants. But when we look at the ratio of the products to reactants, we have to be careful because there's this nonlinear effect that happens. And that nonlinear kind of thing that happens is this. If we look at the numerator is fourth order, square square. But the denominator is third order. You see that? 2, 1. And so that impacts things, you know, differently. You know, if it was fourth order on top, fourth order on the bottom, yeah, then I'd expect it because it's even. But since there's a different impact on product and reactant concentrations because of the fourth order dependence on product concentrations versus third order dependence, let's say, on the reactant, it makes it confusing a little bit. And so maybe the best thing we should do here is to figure out which direction. Is it plus plus minus minus or minus minus plus plus, is to calculate Q. And so let's go ahead and calculate QC and see which direction this should go. And so QC is just going to be the initial concentrations here. And Pretty soon I'm going to just drop the equilibrium in the initial because we can figure it out. Kc is for equilibrium, Qc is for initial. And so plugging in the initial concentrations, the initial concentration of iron is 0.03 thousand. This is going to be squared. Initial concentration of mercury 2 is 0.03 thousand squared, divided by the initial concentration of iron 3, 0.5 thousand. That's going to be squared. And the initial concentration of mercury 1 is 0.5 thousand, but that's raised to the first power, not square. And so this is going to be 0.03 to the fourth, divided by 0.5 to the third. Can somebody calculate our QC value and then see what it comes out to? Is that what you got? And so this comes out to 6.48 times 10 to the minus 6. So it's supposed to be 9, it's 6.5. It's pretty close, isn't it? Would you say that's pretty close? It's pretty close to equilibrium, but it's going to shift which way? This is too small or too big? This is too small. It needs to become a little bit bigger. Not much, but just a little bit bigger, right? To get up to 9.14, which means we need to make more product. In other words, if QC is less than K, then the direction is left to right. And so what we'll see is that, yes, it's kind of close to equilibrium, but it's going to have to shift to the right, even though that K is so small. And so it's going to be minus 2x minus x molar, plus 2x molar plus 2x molar. And so at equilibrium, I'm going to have 0.5 thousand minus 2x molar, 0.5 thousand minus x molar, 0.03 thousand plus 2x molar, and 0.03 thousand plus 2x molar here. And so we'll just plug this into K here. Plug this into K and then solve for X. So this is going to be 0.03 thousand plus 2x squared times 0.03 thousand plus 2x squared divided by 0.5 thousand minus 2x squared and 0.5 thousand minus x to the first. Do you see, do I expect the change to be very much? Do I expect the change to be small?
Yeah.
I expect the change to be small because, you know, Q is pretty close to K. Do you see that? It's really close to K. And so if it's really close to K and the change is small, then do you think the simplifying assumption could work? Well, we could try it. We could just say, you know, 2x is going to be much smaller than 0.03. So 0.03 plus 2x should be about 0.03. 0.03 plus 2x is about 0.03. 0.5 minus 2x is about 0.5. And 0.5 minus x is going to be about 0.5. Does that sound okay to you? I think the change is going to be small. I think it is going to be small, but will the simplifying assumption work here? Because if we drop the 2x here, drop the 2x here, drop the 2x here, and drop the x here, do we have any x left to solve? No. And so the simplifying assumption would fail here because There'd be no x to solve for. And so this is a, what is this? This is a fourth order, is that right? Yeah, this is a fourth order equation. And unfortunately, the Casio FX115ES only goes to third order equations. And so to do this, what would you have to do? Yeah, we could go ahead and try the guess and check method. We could just do the guess and check. And we have limits. For example, x has to be greater than 0, right? But less than 0.25. So just guess a value there and check it. That's one way we could do it. Or could there potentially be another way to solve this? Is there another way to solve this? Now, I don't want to do the guess and check method because it takes time. And so, what else could I try? What didn't I consider? Reset. Maybe I should try to reset it. Do you want to try that, or do you want me to try it? You want to try to reset it yourself? No? All right, I'll reset it for you. So let's go ahead and try the reset. Because the math is kind of complicated, and so if we reset it, maybe that'll make the math easier. And so I'm going to just cancel out these last two rows here and then just try to reset. When I reset it, I want to shift all the atoms to the left or all the atoms to the right. To the left. Why to the left? Because the 10 to the minus 6 means it's mostly reactant. And so this is 10 to the minus 6, so we reset it. And so this is going to be called plus 2y, plus y, minus 2y, minus 2y. And then we look, what's the limiting reactant if we were to have the reverse reaction? We assume 100% reverse reaction. What's the limiting reactant here? Is there a limiting reactant? No, this is called stoichiometric. And so both of these are stoichiometric, so they're both going to be consumed down to 0. And so we're going to take all these iron and mercuries and convert them to these type of iron and mercury. And therefore 2y is equal to 0.03000 molar. And so that means plus 2y is going to be plus 0.03000, and so I'm going to get 0.5000 plus 0.03000, which is going to give me 0.5300 molar. Does that make sense there? And then y is going to be half of 2y, so that's going to be 0.01500. And so 0.5 plus 0.015 gives me 0.5150 molar. And so this will be my new initial conditions. What I've done is I've just moved all the water or all the atoms to the reactant side. That's it. I didn't create or destroy atoms. I just moved them from one side to the other. And so I started off. Let's say if I started off with 100 gallons, I still have 100 gallons of stuff. Now, what is the direction of the change going to be? Yeah, towards the products, towards the zeros. So we're going to go minus 2x, minus x, plus 2x, plus 2x. So this is molar, this is molar, this is molar, molar. And so at equilibrium, I'm going to get 0.5300 minus 2x molar, 0.5150 minus x molar, 2x molar, 2x molar. And so this does make life simpler because over here I have how many binomials? I have 4 binomials over here, right? But with the reset conditions, I'm only going to have 2 binomials and that I have to worry about. And so by resetting it, it makes the math a little bit easier. And so now let's plug this in to our equation here. So Kc is equal to, it's going to be 2x quantity squared times 2x quantity squared divided by 0.5300 minus 2x squared 0.5150 minus x to the first. And so the math is a little bit easier, but it's still a 4th order equation. It's still a 4th order equation, and so I don't have a calculator that does it, and so I'd have to use the guess and check unless there's some other thing I might try to do. And the other thing I could try to do is the
Wait, how would you check it if you're guessing?
Oh, you check it, you guess an x value. And this is the guess and check method. 2x is equal to 6. So my first guess for x is x equals 1. If I plug in x equals 1, then I get 2 equals 6. Well, that's wrong. It's too small. And so my next guess will be, I'll go big. Bigger. X equals 2. X equals 2. 2 times 2 is 4. I'm getting closer. I'm getting warmer, right? And so as I get warmer, what would your next guess be? 2.01? You know, no. Yeah, your next guess would be 3 and 3. Oh, you got it. 2 times 3 is 6. We know what x is. X has got to be 3. And so we do the same thing. We plug in x's here and see how close we are to 9.14. And then we try another x. Are we getting warmer or colder? If we're getting warmer, then we just keep going until we're right on. That's the guess and check method. But hopefully we don't have to do that because it could require a lot of guessing and a lot of time. Because if you think about it, let's say the typical UCLA exam is 50 minutes long. If you use, let's say you use 10 minutes. 10 minutes would be more than 10% of the time. If you use 12 minutes, you've already used 12 minutes, you've used 20% of your time for the exam. You don't have much time left. You know, is 12 minutes very long? You could be guessing and checking for 12 minutes and you've already burned up 20% of your exam time and you haven't even gotten the answer. And so this is why it's so key to have as many shortcuts or ways of doing things as possible. That way you can do it rapidly, because on timed exams, it's a little bit different, the strategy. Versus untimed exams where you got plenty of time, it doesn't matter how long it takes you to solve it. It's okay. But in this case, guessing and checking might take time, whereas I might try to do something else. When I look at this case says all the atoms should be mostly reactant. And so how many atoms will be converted into product? Not much, right? In other words, we expect the change to be small. Let's say we pushed 100 gallons of water to the left and we expect 99.999 gallons of water on the left and 0.001 gallons on the right. Then we expect very little water to flow forward. Here we expect very little water to flow forward because the atoms are biased towards the reactants. And so I could use the simplifying assumption here, right? I might as well try it. And so try the SA. The reason we couldn't use the SA before is because x completely drops out. But in this case, x will not completely drop out because 2x compared to 0 is significant. Anything compared to nothing is significant. Even if it's a minuscule amount, it's going to be significant. And so we're going to try the SA. Now when we try the SA, we're going to assume this. Well, we got two of them. But let's pick the bigger percent change. If we lose 2x from 0.53 versus x from 0.515, which one is a bigger percent change? In other words, which one is taking a bigger bite out of the pool? The 2x or the x? But the pool size is different. This is a 0.5300 pool. This is a 0.5150 pool. And so which one is a bigger chunk out of the pool, percentage-wise? You know, why I'm saying this is one drop. If you remove one drop from a big swimming pool, the percent change is nothing. But if you remove one drop from 3 drops, you've just lost 33. You've just lost a third of your water, right? If you remove one drop from 2 drops, you've lost half your water. And so this is a 50% change versus a negligible percent change. So we don't look at x. I know 2x is bigger, but we got to look at what you're taking it from. And so which one is a bigger percent change? 2x from 53 or x from 51? X from 5150? Well, 53 and 51 are close. And so it's actually going to be 2x from 53 is going to be a bigger percent change. And so what we'll say is 2x is going to be much smaller than 0.53. If 2x is much smaller than x, is definitely got to be a lot smaller than 51. Does that make sense? We'll do a calculation to prove that later. All right, if we do that, then this is going to do this. This is going to simplify to 2x squared divided by 0.5300 minus 2x will be 0.5300. We'll square that. And then 0.5150 minus x will just be 0.5150. And we'll raise that to the first power. And so this is going to give me 4 times 4, 16x to the 4th divided by 0.5300 squared times 0.5150. Now look at the math. Is that math easy or what? All you need to do is hit the square root key twice, right? And you can get the 4th root of this. And what does x come out to? So it would be 9.14 times 10 to the minus 6 times 0.53 squared times 0.515 divided by 16 square root square root. 0.01695. We're allowed 3 sig figs, so we'll go 0.01695. Is that what everybody got?
Yeah.
Okay, we're good. Now we have to justify this. And so we're going to justify it, but we have 2 changes here. Which one should we pick? And so let's just take a look at both of them. We always pick the bigger one because, you know, that's the one most likely to fail. And so the percent change is going to be the change over the initial times 100%. What is the change? The change here is 2x. And so this is going to be 2x over 0.5300 times 100%. And so can somebody calculate this percent? 6.398%. Thanks. Oh, this is no good, right? Because this exceeds our 5%. So is the simplifying assumption valid or invalid? Invalid. But maybe for the other one it might be valid. And so let's go ahead and calculate the percent change for the other one. The percent change for the other one was x over 0.5150 times 100%. Actually, there's no reason to calculate this. Why? Because if it fails for this one, it's done. You can't use it, right? And then this one's going to be what percent? 3.29? And so the problem is that some people accidentally calculate it for the wrong one and say it's okay. But if it works for this one and fails for this one, can we use it for both? No. Maybe if it works for this one, we can go ahead and use it for this one, right? But that still means we got a fourth order polynomial we got to solve, which isn't easy. And so it doesn't really help us. And so it doesn't matter that this one is less. It failed here. Is that clear? And so this is why we only calculated for the biggest percent change. We got to see the biggest percent change is the one that's most likely to fail. So was this a complete waste of time? No, because if we're going to do guess and check, what would you rather do guess and check with? 4 polynomials or 2 polynomials? 2. And so if we're going to do guess and check, it's best to do guess and check on this one and plug it into this ICE table rather than the previous one in this ICE table, right? That's number 1. And number 2, this is not a waste of time because even though this x value is too far off, it's closer than taking a random guess between 0 and 0.25, right? If you were to take a random guess between 0 and 0.25, would you have come up with this number? Probably not. But this number is going to be close because, I mean, it's not that far off. Okay, that's number 2. Number 3, it's not a waste of time because you save problems like this for last. And so once the time runs out on the exam, it's better to have some answer and say, well, it's exceeding it, but the equilibrium values are going to be close to, and you can calculate it so you can get some final answer with a caveat that it's going to be off a little bit, right? That's better than leaving it blank. And so this wasn't a waste of time. But now, well, we have time, so if we have time, we should try to get a better answer, right? If we ran out of time, maybe we'll just live with this and make a little note. Uh-huh.
So can't you use that x value and guess around there?
Yeah.
So you guess less.
Right. And so this is going to, this is good because this x value is going to be a perfect first guess, don't you think? And so it fails. So the simplifying assumption failed. But we'll use this as our first guess. But when we're doing guess and check, I don't want to punch in that many keys in the calculator. And so my first guess. Okay, so we must use method of successive approximations in Appendix A. If you want to read about it. It's such a simple method, you don't really need to read it to understand it. And so the first guess, x, this is 4 digits. Don't really want that. Just maybe make it simpler. Let's go 0.017. So it's less keying in the calculator. And so this is going to be our first guess. Let's calculate k based on this equation. And so we plug in 0.017 times 2, square that. Actually, you know what? Let's make this a little bit easier. To make this a little bit easier, let's go 16x to the 4 divided by 0.5300 minus 2x squared 0.5150 minus x. And so the way I just do this is I just do 16x to the 4 over 0.53 minus 2x squared, because we don't care about sig figs yet. 0.515 minus x. Just do this. And so I'd probably do it like this. I'd probably go, what would I do? I'd probably do 2 times 0.017 is 0.034. So I'd do 0.53 minus 0.034 equals square times parentheses 0.515 minus 0.017, close parentheses equals, invert it, times 16 times 0.017 squared squared, or 0.017 to the 4. And what do you get? All right. I'm going to move the decimal. So that's 10.9 times 10 to the minus 6, which means we're just slightly too big. You know, we need to bring this down a little bit. And so for the next guess, you know, this is the 4th, this is the 3rd. Let's make it smaller. And so let's try 0.016. And then with a 0.016, let's recalculate what k is. It failed, but it's close. And so what we want to see is it failed, but is it too big or is it too small? That's what we need to find out, because we know it failed because the amount of error that's in there. And so what we figure out is 0.0169, which is close to 0.017. Well, that came out here too big.
Don't we know we need to be between 0.01695 and between 0.017?
No.
I got 8.473 to the negative
8.473 times 10 to the negative 6. Okay, now we went too small. And so now we have to go bigger. So this is 8.5 to 10, 11. 8.5 to 11, where do you want to go? Next. You just got to go 9. So
You go into the 10,000s.
yeah, let's go 0.016.
3?
3?
Yeah.
All right, let's try 0.0163. Recalculate k. The reason it wouldn't be between 0.0169 is because we don't know what the k value for 0.0169 is, actually. You know,
9.154 times 10 to the negative
9.154. Wow. Times 10 to the negative 6? That's close, but is it close enough? No, we want 9.14. So this is just a little bit too big. And so what do you want to try next? 0.162? Okay. Try 0.0162.
I got 8.92 times 10 to the negative 6.
Okay, you know, we went way too small. We just need to go a tiny bit lower than 163. Do you see that?
Yep.
And so, yeah, let's try 01629 or 8. What do you want to do, 8 or 9? 8, all right. Try this, 0.01628, and see what your K comes out to.
9.1075.
9.1075. It's still too small. Okay, let's try 0.01629. See if that, yes, that's there.
9.13
9.13.
times 10 to the negative
What comes after 3?
1308.
0. I was thinking if it rounds, we would be okay, but it doesn't round to 9.14 times 10 to the negative 6, right? And so we're just slightly too small. And so what we have is, we have 1630 is slightly too big, and 1629 is slightly too small. So what do you think? Yeah, maybe right in the middle. Let's try that. 0.016295, right in the middle. Give that a shot and see what it comes out.
$9.14249.
9.142.
Times 10 to the negative 6.
Actually, we have 5 digits here. We can carry that. Times 10 to the negative 6. Wow. So is this enough?
Got another one. Let's go to the next one.
I mean, we could go to another one, but there's going to be a point because, you know, pretty soon you'll be at 9.1408, and then you go, you know what, I want to go to 9.1400. You know? And so you gotta stop somewhere, right? And so where can you stop? Well, we can stop here because this rounds to 9.14. I mean, we only have 3 sig figs there. That's number one. Number two is, you know, once we start changing the digits, you know, because this is going to be 0.5300 minus 2x. Once we start changing the digits, like 0.50, like this over here, 0.5300, and we start changing this digit, is it going to make really any impact on this? You know, no. And so, you know, we have 4 decimal places here. 5 decimal places, yes, because, you know, that's rounding and that type of stuff. But 6 decimal places, when we get to maybe the 6th or the 7th decimal place, does it really make any difference in the subtraction here? No. And so how many decimal places are we out? 1, 2, 3, 4, 5, 6 decimal places. And so it's starting, if we go to the 7th decimal place, it's really not going to make much difference when we round our final answers. Do you see that? And so here, it's okay to stop. If you want to keep going, you have extra time, keep going. You probably can get it right on. I mean, right on meaning 9.140, something, 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 you know, if you want. But this is good. And so this is a pretty good value of x. It didn't take us too long. And so let's go ahead and go back over here and then do the calculation. It's going to be 0.5300 minus 2x. And so can somebody double this? Tell me what we come up with. Actually, we're running out of time here. And so what you're going to do is you're going to just plug this back into here, right? Because this K expression was based on this ice table, not this ice table, right? This is our original ice table. It had a different K expression. The X are different. The X's are different. And so you plug this back in here and you do your double check. And when you do your double check, hopefully it comes out to, actually it should. It's going to come out to, it should come out to 9.1429 because you just did it, right?
Yeah.
It should come out to that, but because of rounding, right? Maybe there's some rounding. Well, anyway, just double check it, even though it's circular. Are we good with this? So you can complete this at home here.